Hello everybody and welcome to this video where I'm going to propose to you to go through the steps necessary to derive Kirchhoff voltage law starting from Faraday law. Again, I need to correct this. Okay. So from Faraday's law, the Faraday law of induction is also called, to Kirchhoff voltage law. And as we discussed many times, the idea is that by going step by step through the necessary assumptions we need to take in order to be able to derive Kirchhoff voltage law from Faraday law. If we do that, we will understand what could be the mistakes we do when applying Kirchhoff voltage law when it cannot be applied. And then, we always argue that those can be most of the time the nature of EMC problems. Before we start with Faraday law, a little bit of a recap, because now we are going to Faraday law deals with electric fields mainly, and Kirchhoff voltage law deals with voltages. And what is the relationship between a voltage and an electric field? So imagine we have an electric field here. Somehow it's distributed in space, doesn't really matter. This is just an schematic. So this is an electric field over there, and we define a point in space. Here, this point is called A, another point which is called B. Now we know that due to this electric field, this point B will be at a certain potential, a potential B, and here there's also a potential at point A. This potential is due to the electric field that is present everywhere. Now we are interested in knowing what is the difference in potential, what's the delta V between point A and point B. Sometimes this is between B and A, it depends how you want to estimate that. So basically, to calculate this, what we need to do is calculate minus the line integral between A and B of this electric field everywhere, following a certain path of integration. So the way we connect A to B, apparently it matters. So let's say I define a path of integration that goes this way. It goes from A to B like this. So my dl is a small vector that looks like this. And if I do this calculation, I can estimate the difference in potential between point A and point B. Now let's continue this exercise. Think, for instance, if there is another point C over there, and I can also calculate what's the difference in potential between B and C, and it will be clearly minus the line integral between B and C of E dot dl. And in the same manner, let me just for completeness draw this path over here, certain path with this dl. And if we want to close the loop, for instance, we can also estimate what is the difference in potential between point C and point A. This is easily calculated as minus the integral between C and A following a certain path of E dot dl. There you go. And this is the path that we would like to integrate, and this is our dl over here. Just a recap how potentials are defined. The potentials are defined as the line integral of the electric field. Now let's go to the juice. Let's go to the real thing. To be able to understand how Kirchhoff voltage law was derived, we need to start with Faraday law. It's easier if we work with Faraday law in integral form. We know that the closed line integral of the electric field dot dl in a certain region of space. Faraday law of induction tells us that this is equal to minus the time derivative of the magnetic flux in a certain area. Which area? Well, the one that is enclosed by the closed circuit integral of this electric field. Now, if we apply this integral over here and to this simple schematic I just did, so we can break down the integral, the closed integral of the electric field into three integrals: one from A to B, plus one from B to C, plus another one from C to A again. So this closed integral can be written as the integral from A to B of the electric field dot dl, plus maybe this could be a dl1, but it doesn't matter. This from B to C of the electric field dot dl, plus, and then now in this example I only use 3 branches to close the loop, but clearly I could have used infinite, any number, potentially infinite number of branches. So I will generalize this to as many branches as you want. Let's say from letter x n minus 1 to xn. Those x is just a letter from A to B, etc. So the E dot dl, there you go, and this still is equals to minus the time derivative of the magnetic flux in the area we are enclosing with all those integrals. Now if we apply what we saw before, and we can change the signs and things like that, but it's easy to see that this will be something like the voltage drop between B and A. Because if we replace the negative sign over here, we need to change the integral intervals a little bit here. So this is the voltage drop between B and A. This will be the voltage drop between B and C, and this one will be the voltage drop in the branch, in the nth branch. So the voltage drop between xn and xn minus 1. Or if I write this down in a more complex, in a more compact way, we can say that the sum of all the voltage drops in a mesh, the sum of all the voltage drop in a mesh equals minus dt, the flux integral of my magnetic induction field. Now you can see that we are pretty close to Kirchhoff's law. The only thing we need to do now is that we should make sure, or we should find a way that this number over here is equals to 0. Because Kirchhoff's voltage law indeed says that the sum of all the voltages in a mesh or in a loop equals 0. But Faraday law says it's not equal to 0, it's equal to the rate of change of the magnetic flux in that area. How can we make this 0? Well, the trivial way is to integrate in a surface that is 0, but then surface 0 means no loop at all. So that's a solution we are not interested about. The other possibility is to have this will be 0. This will be 0 if this integral is 0, and that means that dB dt has to be equal to 0. Again, we end up with another condition that we need to specify for Faraday law to be, in order for Kirchhoff voltage law to be valid. And these conditions are again static or quasi-static conditions. In other words, there are no changing magnetic fields. If there are no changing magnetic fields, then we are allowed to make this integral equal to 0, and that means that the sum of all the voltage drop in a closed loop or in a mesh equals 0.